So the Fibonacci sequence is kind of a fun sequence that shows up. It has some really interesting properties to it. So let's define f sub 0 to be 0, f sub 1 to be 1, and f sub n to be f sub n minus 1 plus f sub n minus 2 for n greater than or equal to 2. So basically we have two initial terms. F sub 0 is 0, f sub 1 is 1. And to get the nth term for n greater than or equal to 2, you take the previous two terms and add them together. So for example, just write some terms of the Fibonacci here. F of 0, 0, f of 1 is 1. So how do I get f of 2? Well, I'm going to add the previous two. I'm going to do 0 plus 1 and get 1. And how do I find f of 3? Well, I add 1 and 1 to get 2. How do I find f of 4? Well, I add the previous two terms, 1 and 2, to get 3. How do I find f of 5? Well, I add 2 and 3 to get 5. How do I find f of 6? I add 3 and 5 to get 8. How do I find f of 7? I add 5 and 8 to get 13, and so on and so forth, right? The Fibonacci sequence, pretty cool dude. So we want to look at some pretty neat problems that you can do with the Fibonacci sequence. This is a show that if I take the Fibonacci terms, f1 squared plus f2 squared plus f3 squared, so on and so forth, fn squared. So if I add up the squares of the first n Fibonacci terms, I get f sub n times f sub n plus 1. So let's show that. So here we go. We're going to do a little proof of this. So first of all, we know how the Fibonacci is defined. If I were to look at f sub k, the kth term, that's going to be the k minus 1th term plus the k minus 2nd term. So that implies that definition of the Fibonacci recursively defines that f of k plus 1, the kth plus 1 term is going to be the kth term plus the k minus 1th term, right? K plus 1 is k plus k minus 1 term. Now what we're going to do here, we're going to solve for f of k. Solve for f of k. So f of k here, if I get it by itself, it's going to be f of k plus 1 minus f of k minus 1. So basically I just kept this guy. I got this guy by itself, f of k by itself. So this is the really important identity that's useful for calculating things with the Fibonacci sequence. I sometimes say that the present, right, the kth, is equal to the future, the kth plus 1th, minus the past, k minus 1. So I call this right here, the present is equal to the future minus the past. So that's something you want to remember about the Fibonacci. The present term is equal to the future term minus the past term. Okay, so really useful. So now we're going to go on. Scroll a little. Let's look at f1 squared, f2 squared, f3 squared, and so on. let's look at fn minus 1 squared all the way up to fn squared, right? We want to add up all the squares of the Fibonacci all the way to the fn term. f1 squared, f2 squared, f3 squared, all the way up to fn squared. So what do we have? We can write this as f1 times f1 plus f2 times f2 plus f3 times f3 plus so on and so forth, fn minus 1 times fn minus 1 plus fn times fn. Now I'm going to focus on the second fn terms. f1, f2, the ones I'm putting in red, f3, fn minus 1, and so on and so forth, fn. So I'm going to leave the green alone, and I'm going to actually replace f1 using this identity back here that the fk right here is equal to fk plus 1 minus fk minus 1. So the present is equal to the future minus the past. So f1 is going to be the future, f2 minus the past, f0. Then we go on to plus f2, and then that red f2 we're going to replace with a red future minus the past, f3 minus f1. Okay, then we're going on to the green, f3. Now the red f3, we're going to have f3 is the future, f4 minus the past, f2. And you keep going. So on, so forth. Now we're going to go on to fn minus 1 times a red fn minus 1. Well, rather than writing red fn minus 1, we're going to write the future fn minus the past, fn minus 2. And then we go on plus fn in green, and then that red fn, we're going to replace that red fn with the future fn plus 1 minus the past, fn minus 1. So let's actually now multiply this out a bit. I'm going to distribute my green f1 through the reds. I'm going to get f1, f2, minus f1, f0. Okay, now we're going to distribute the green f2 through the f3 and f1, plus f2, f3, minus f2, f1. And then we're going to distribute the green f3 through the f4 and the f2. We're going to have f3, f4, minus f3, f2, so on and so forth. Okay, let's scroll. And now at this point, we want to distribute that green fn minus 1 through the two reds, fn and fn minus 2. So we're going to have what? Fn minus 1 times fn minus fn minus 1 times fn minus 2. And finally, I distribute my green fn through the fn plus 1 and the minus fn minus 1. I'm going to have fn plus 1 minus fn minus 1. So we've expanded everything. Now let's see, are there any cancellations? Well, here I have f1, f2 cancels with minus f2, f1. Okay, here I have f2, f3 cancels with minus f3, f2. So you can imagine that this f3, f4 is going to cancel with some kind of minus f4, f3 somewhere within these dots. Now, looking on the other side, past those dots on the right, we have what? Fn minus 1 fn cancels with minus fn minus 1. Then it looks like this minus fn minus 1, fn minus 2 here is going to cancel with something here inside of these dots. something ahead of it. So essentially what we're left with just a few terms. We have minus, come on blue, you're supposed to work. It's not working, totally not working. Minus F1, F0 fails to cancel. Right, there's nothing before that to cancel out that minus. And this positive right here, Fn plus 1, there's nothing negative behind it to cancel it. So we're left with negative F1, F0 plus Fn plus 1. So let's remember, what was minus, or what was F1? F1 was 0. 1. F1 was 1. F0 was 0. So we have negative 1 times 0 plus Fn plus 1. So we're left with, this zero's out right here. We're left with Fn times Fn plus 1. And that's what we wanted to prove. So I'll put a little box here to say we're done now. All right, that's a pretty neat little thing. Right, that's what we wanted to prove. We wanted to prove it was Fn times Fn plus 1.